Yes, welcome to my talk on river reach mapping with UAVs, and it's in collaboration with colleagues in Finland and Hungary. And we are we are trying to map entire river reaches with UAVs, and not just surface velocimetry, but also the bathymetry, and to eventually be able to estimate the discharge. And we are looking at 3 different reaches, one smaller one in Germany with a length of about 300 meters on the left, and then in the middle in Hungary, another river with a length of about 600 meters. And the largest reach is mapped in northern Finland, which has a length about 1 kilometer. And we are now here capturing data at each site with DJI UAV products. And in the first step, we are doing a standard structure for motion photogrammetry to get the topography of the river reach. And as you can see now here in these maps, if the water is clear enough, it's also possible to reconstruct the points under the water. But if you would now use these points as they are, then that would be indicate, or then you would have an error in your underwater points, because usually these standard structure for motion photogrammetric tools do not consider the refraction, which means that the ray of light is changing direction when it changes the media, and in this case, when it changes from water to air. And as you can see in this image here, if you do not consider it, it's shown here in blue, then you would underestimate the water depth, or vice versa, you would overestimate the height of your points under the water. But if you do know the pose of the camera as well as the water surface, then it is possible with different approaches to indeed correct this effect, and you can model it, and then you can calculate your underwater points correspondingly. And in addition to the bathymetric correction of the points underwater, we also developed a workflow to improve the visibility of the riverbed under the water. So as you can see in this image here, we want to remove these wave shadows and to be able to also see underneath. And what we are doing, we are capturing video frames and we are co-registering them to account for the movements of the UAV. So at the end, it looks like we are always looking from the same perspective. And then we can calculate an averaged image. In our case, we are using the median. And as you can see in the bottom now, that's the filtered image, that it's indeed you increase the visibility of the points underwater. And as a result, you can see now here the bathymetric reconstruction at all 3 sites. And we were able to reconstruct water depths up to 1.65 meters. And afterwards, it's more difficult because the water is too deep and you're not seeing the bed anymore. And also at sites as it's in the middle at the river reach in Hungary, there are also larger data caps because of turbid conditions of the river. So you really need to have clear water conditions to perform this kind of mapping. And as you can see on the right side, in Finland, we had very clear water, and it was very well possible to get there the bathymetric information. And if we then have the bathymetry in the next step, we also, of course, want to get the surface flow velocity. In our case, we are using PTV. And I just very quickly will go here through the workflow and illustrate it now for having a hovering position, as you can see now here at one cross section. And then we just again use the image co-registration to indeed enable just looking from one perspective. It's the same which we used to calculate the median image, but this time we are not interested in the average, but indeed every frame to then trace the particles. And afterwards, when the frames are co-registered, we mask the shore areas so that we indeed are really only looking at the water area and to detect then features on the water surface, which we then want to trace in the next step. And this in this case here is, for instance, using Harris corner detector from image processing or computer vision enables us to detect these features. And then we are using the Lucas-Kennedy algorithm to trace the features from one frame to the next. So which is based on that you are searching for parameters of an affine transformation in such a way that you're minimizing the gray value differences between the patches. And then you can trace your particle through the frames as indicated here for this short video sequence. And in the next step, we also do some post-processing of the traced particles because there are still outliers due to ambiguities, for instance. And in our case, we are looking at the main flow direction, or we're doing assumptions about the flow, and then we say, okay, that's the main flow direction, and the traced particle is not allowed to move too strongly from that main flow direction, or as well as the steadiness of the particle. We consider that as another parameter to filter out outliers, and also that the particle has to be traceable across a minimum number of frames. And with this information, we have then our filtered velocity tracks. However, at the moment still in pixels per second. And in the last step, we have to convert that then into meters per second by georeferencing our measurements. So if we know from which position and orientation the frame was captured, we can then project these image measurements through the camera projection center into the object space and intersect it with the water surface, and then get our needed information. And this is now illustrated for one steady hovering UAV position. And this approach we then extended for the entire river reach, as shown now here. So we were flying with a drone slowly along the river reach and capturing a video. And then in the next step, we are extracting so-called head frames after a specified time interval, and also corresponding tailing frames, which we then co-registered as already illustrated. But then we include these head frames in a standard structure for motion photogrammetry workflow. So this allows us that we do not have to set up ground control points just for the UAV flight of the video along the river. And so we implement these head frames into the structure for motion approach to get our frame position and orientation. And this we use then in the next step to estimate the water level. So we then can say for each frame's field of view, we can get the water level information. And we do that from the bathymetric point cloud, or the border of the bathymetric point cloud. And also we use the bathymetric point cloud to project it then back into the image in each of these head frames to mask the water area, to then again being able to detect the particles and trace them through the frames. And here you can see the corresponding result of this processing. So for each river, it's now possible at our 3 different sites, we are able to get the spatial velocity pattern across the entire river reaches. And as you can see, you can very well capture the spatial variability along the river reaches. And of course, then we also did some accuracy assessments with to see how accurate we could get with our data. And we used at the German side current meter measurements, and indicated here in blue dots. And on the other 2 sides, we used ADCP measurements, indicated with white dots or cross sections. And then we compared the surface velocities with the ADCP measurements. And as you can see, here are the results for that. And our average deviation ranges between 0.03 meter per second to 0.08 meter per second. And now these were the measurements we were doing with RGB. And in the next step, we are also now trying to use thermal infrared imagery. So these are first results now indicated, this time only for hovering position, but we want to extend that also to the reach of as well later on, because the idea is to densify the surface velocity observations in scenarios where we might have not as many particles on the surface to track. So in this case here, again, we are at the Hungarian site, and we capture with a FLIR camera at a height of about 60 meters frames every half second. And then again, as you can see here, due to this half second only, you see very strong movements of the UAV. So again, we did co-registration, but we also did a further step, because if you look now here in the water area, at the moment, you do not see any signal, thermal signal of any flow. And this is because you also see the shore areas. And then as the gray values are stretched over this long range. And though we also have to mask the shore again, so we are able then to stretch our gray values really only within the water area and to increase the signal. And if you look now closely, you can already detect some flow within the river, and which we then enhanced with some further image processing, like the adaptive histogram equalization to improve the visibility. And then in a last step, we are using in this case then PIV instead of PTV. As you can see on the left, the results of our first assessments, and on the right, the corresponding RGB image measurements. And this now we want to take in the next step also for entire river reaches. And if we have now the surface flow velocity information as well as the bathymetric information, we want to go, of course, then the next step to also extract the discharge. And here it's now shown for 3 cross sections, which we selected. And the nice thing is, if you have now this densely information of the velocity and bathymetry, you can indeed choose locations which you think are most suitable for discharge estimation. So, and here it's now shown for cross section 2 at the right side, just a snapshot. And as well, you can see now on the table the discharge measurements with ADCP reference and based on our UAV data. And the results look promising. However, it has to be noted, especially if the cross sections are very wide, then this approach is very sensitive to the accuracy of the water level estimation. So as in this case, if you're only off by 2 centimeters with the water level, then the discharge is going to be decreased by 50%. So this is something to consider further. But now it is indeed possible to extract cross sections along the river reach with a lot higher density. And so this could be also a future way to maybe address this issue by having a better statistical grasp of the estimated discharge based on what location you're at.
2 minutes, Annette.
Yeah. Yes.
Oh,
thank
perfect.
You. Yeah.
Oh, so I feel really bad there that I jumped in just as you were about to finish. But there's a number of comments reflecting my own views that's really excellent presentation, really exciting work. So I won't hog the questions this time because a couple came through in the chat. Firstly, from Kirill, is there a threshold of turbidity or wave roughness beyond which optical bathymetry no longer works?
Yeah, it's a good point. For sure there is, but I'm not able to say that yet, because in our scenarios we were looking at we had quite comfortable conditions, and but of course there is going to be it's not going to work if it's turbid enough. But in this case we are doing repeated measurements at these sites, so I hope we will get a better grasp if we can at least site specifically say at what condition it's not possible anymore.
I think it will be good to quantify this, because we questions normally asked people may use this amazing technology.
And also related is whether there's presence of algae on stones on the river bottom corrupts the determination of the bathymetry.
It's a good point. In our case, we were not yet paying too much attention to that aspect, but it's a good point for the next time to also look at it. But in our case, we have not encountered an issue with this yet, but it has to be noted in general that also we do these corrections. These reconstructed points underwater are still noisier compared to the one above the water surface.
Okay, and now I'm going to squeeze in one last question because you were quick. What software are you using for your SFM DEM structure from motion digital elevation model construction? And what's the uncertainty?
In this case, well, we used standard Metashape Archisoft approach to process the data, and the uncertainty then of course depends on how your ground control points are distributed, what camera you're using, what flight pattern you're using. Those all these kind of things play into it, but you can indeed perform accuracy assessment based on these observations.